Problem 4.44 is a Young's modulus problem. We're given the Young's modulus of aluminum, which is given as 6.2 times 10 to the 10 newtons per meter squared. The density of aluminum is given as 2.7 grams over centimeters cubed, and the molar mass of aluminum is 27 grams. And what we're trying to find the spring stiffness of hold on. Alright. In this problem, we're modeling the interactions of the neighboring aluminum atoms as if they were connected by springs, like in this beautiful picture right here. And what we're trying to find the spring stiffness of the little springs connecting each atom. So first, we're going to convert the units of the density and the molar mass to kilograms over meters cubed and to kilograms. Just ignore this right here. So for density, we're going to go from 2.7 grams over centimeters cubed. To cancel the grams, we're going to multiply by kilograms. 1 kilogram over 1,000 grams. Let's cancel this out the grams. And now we multiply by centimeters. Actually, 1,000,000 centimeters cubed per meter cubed. And that's because there's 100 centimeters in a meter, and since it's cubed, it's going to be 100 cubed. So this gives us 2,700 kilograms over meters cubed. For the molar mass, simply 27 grams in 1 mole, and we simply divide by 1,000. So 1 kilogram is 1,000 grams. So this gives us 0.027 kilograms per mole. Now, since we have the density and the mass, we can find the volume, which is mass over density. So volume equals mass over density, which would be 0.027 kilograms 1 mole, divided by density, which just multiply the reciprocal of the density, would be 1 meter cubed over 2,700 kilograms. Kilograms cancel out. And we're trying to find the volume of one atom, so we have to cancel out the moles as well. So multiply 1 mole over Avogadro's number, 6.02 times 10 to the 23rd. And that gives us 1.66 times 10 to the negative 29 meters cubed per atom. Now, if we go back to our drawing here, the volume of the little cube right here of the springs would be d times c, which would be d cubed. So this volume also equals d to the third, which means that d equals v to the 1/3, which would be the cubic root of 1.66 times 10 to the negative 29, which gives us 2.55 times 10 to the negative 10 meters. That's for D. Now, at the micro level, the formula for Young's modulus is Y equals the spring stiffness over D. Now, the Young's modulus was already given to us in the beginning, which was 6.2 times 10 to the 10, and we just solve for D, so we can just solve for the spring stiffness so we can get our answer. So spring stiffness equals Young's modulus times D, which equals 6.2 times 10 to the 10 newtons over meters squared times 2.55 times 10 to the negative 10 meters, and that gives us 16 newtons over meters. For part B of this problem, we're going to do everything we did for part A, except it's for aluminum. And for aluminum, the Young's modulus that is given is 1.6 times 10 to the 10 newtons per meter squared, and the density of lead is 11.4 grams over centimeters cubed, and the molar mass of lead is 207 grams per mole. We can convert the units for the density and the molar mass of lead by using the same steps we did in part A. So for the density, we would end up getting 11,400 kilograms per meters cubed, and for the molar mass, we would get 0.207 kilograms per mole. Next, we solve for the volume of the lead, which would be the mass over the density, which would be 0.207 kilograms for 1 mole times the reciprocal of the density, which would be 1 meter cubed over 11,400 kilograms. Kilograms cancel out, and we multiply by 1 mole over Avogadro's number to cancel out the moles. And we end up with 3.02 times 10 to the negative 23 meters cubed per atom. Now, as we stated earlier, the volume equals D cubed, and D equals volume to the 1/3. So that means that for lead, D equals the cubic root of 3.02 times 10 to the negative 23rd meters cubed, which would give us 3.11 times 10 to the negative 10 meters. Now, using the formula for Young's modulus for the micro level, we get that the spring stiffness equals Young's modulus times D. So we use the Young's modulus given for the lead, which is 1.6 times 10 to the 10 newtons over meter squared, times D, which is 3.11 times 10 to the negative 10 meters, and this gives us 5 newtons per meter as the spring stiffness.